Welcome to Fantastic Vision. Please subscribe us before you watch today's video. In the recently released Guidelines for the Promotion and Application of the First Major Technical Equipment, 2024 edition, the Ministry of Industry and Information Technology clearly proposed a new milestone in China's lithography technology. The document specifically mentioned the latest progress in the field of integrated circuit manufacturing, including two categories: krypton fluoride lithography and argon fluoride lithography. This update emphasizes the application of krypton fluoride (KrF) and argon fluoride (RF) lithography, both of which use deep ultraviolet (DUV) technology. Argon fluoride lithography is particularly eye-catching, and its core technical indicators include 193 nanometers light source wavelength, minimum resolution of 65 nanometers, and overlay accuracy of no more than 8 nanometers. The specific meanings of these technical parameters are as follows. 193 nanometers light source. Currently, lithography technology has developed to the 5th generation. A brief overview is as follows. First generation, G-line lithography, with a light source wavelength of 436 nanometers, is mainly suitable for the production of chips with specifications of 350 nanometers and above. Second generation, I-line lithography, with a light source wavelength of 365 nanometers, is designed for 350 nanometers chip manufacturing. Third generation, krypton fluoride, KrF, lithography machine, with a light source wavelength of 248 nanometers, capable of producing 130 nanometers chips. Fourth generation, argon fluoride, RF, lithography machine, with a light source wavelength of 193 nanometers, with basic production capacity covering up to 65 nanometers chips. After adopting immersion technology, the effective wavelength can be reduced to 134 nanometers, supporting the production of 7 nanometers and finer chips. Fifth generation, EUV lithography machine, designed for chip manufacturing below 7 nanometers, currently tsmc. Samsung and others use ASML's EUV lithography machine. The wavelength of 193 nanometers belongs to the deep ultraviolet region, which indicates that China's lithography machine technology has stood on the threshold of the 4th generation. 65 nanometers resolution. The resolution of the lithography machine reflects its ability to clearly project and distinguish adjacent graphics on the silicon wafer. Resolution can be calculated by the formula resolution equals K1 times na backslash text. A resolution equals K1 backslash times backslash fracka backslash lambda na. A resolution equals K1 times na, where K1 is a constant, lambda backslash lambda is the wavelength of the light source, and na is the numerical aperture of the objective lens. Improving the numerical aperture of the objective lens is the key to improving resolution and manufacturing more precise chips. Taking ASML as an example, the Na of its DUV lithography machine has been increased from 0.4 to 0.93, and the EUV lithography machine has increased from 0.33 to 0.55. These upgrades have significantly improved the manufacturing accuracy of chips. As far as the current situation is concerned, although the resolution of ASML's DUV lithography machine has reached 34 nanometers, the resolution of domestic lithography machines has reached 65 nanometers, which shows the important progress made by domestic technology in catching up with the international frontier. Multiple exposure is actually a composite exposure technology that improves the resolution without changing the wavelength of the light source, thereby producing more advanced chips. For example, TSMC used a 1980 Di type lithography machine with a wavelength of 134 nanometers to produce the Kirin 990 chip with a 7 nanometers process for HUAWEI, which is the result of the use of multiple exposure technology. At present, Common multiple exposure technologies include exposure curing, exposure etching, LFLE, double exposure, LELE, triple exposure, LELE, and self-aligned multiple patterning, SAMP, and other technologies. Double exposure technology can significantly improve the image quality of 28 nanometers chips, making it equivalent to 14 nanometers. Triple exposure and self-aligned multiple patterning technologies are more used in 16 nanometers, 14 nanometers, and 7 nanometers processes. In the multiple exposure process, the accuracy of overlay is particularly critical. The position of each exposure must be aligned very accurately, otherwise it will cause circuit structure errors. So the position offset of the two exposures is an important criterion for measuring overlay accuracy. In addition, multiple exposure also means increased costs, and it will also affect the production efficiency, yield and power consumption of the lithography machine, resulting in higher costs. In theory, an overlay accuracy of less than or equal to 8 nanometers can produce 8 nanometers chips, but in actual production may be abandoned due to cost and yield issues. For example, if the cost of a batch of 8 nanometers mobile phone chips is as high as 1,500 yuan per chip and the heat is serious, its practical significance will be greatly reduced. Moreover, the resolution of domestic lithography machines is currently 65 nanometers, which is still a certain distance from Zeiss's objective lens. Therefore, domestic RF lithography machines using immersion technology should be able to produce 14 nanometers chips at present, which is already a considerable breakthrough. At present, chips with 14 nanometers and above processes are widely used in aerospace, military, automotive, industrial and home appliances, with a market share of up to 70%. Advanced chips of 7 nanometers and below are mainly used in smartphones, advanced CPUs, supercomputing, AI chips and autonomous driving, with a market share of about 30%. Therefore, the advent of domestic argon fluoride, RF, lithography machines is expected to significantly increase the self-sufficiency rate of China's chip industry to 70%, and it is expected to achieve localization of 7 nanometers chips within 2 to 3 years. Globally, the only countries that can independently develop lithography machines are the Netherlands, Japan and China. ASML of the Netherlands is a leader in lithography machine technology. Its products integrate global technologies, such as light sources from the United States, objective lenses from Germany, bearings from France, and also use some technologies from Japan and Taiwan, China. It is reported that ASML has as many as 3,000 suppliers all over the world. Although Nikon of Japan is closely behind ASML in terms of technology, it cannot be completely independent and is restricted by European and American technology. China is the only country that relies entirely on independent research and development, because in terms of lithography machines, the export of parts and components is prohibited to China. This is enough to prove that key core technologies have been 100% localized, which is not available in other countries. But we should also see that the road to lithography machine technology is still full of challenges. The next generation of EUV lithography machines has higher requirements, and the requirements for light source technology, objective lens system, double workbench, bearings, cables, etc. are more stringent. The need to use 13.5 nanometers extreme ultraviolet light source technology, an objective lens that is 100 times smoother than a bathroom mirror, and a double workbench with nanometer level errors, etc. All of which sound suffocating. Once these technologies break through, the global chip industry landscape will be completely overturned, and ASML's leading position will also be lost. From the early ASML engineers mocking China for, even if the drawings are made public, they can't make it, to the later, China can't make advanced lithography machines, to last year's ASML president Wenninke saying China's independent research and development of lithography machines has destroyed the global industrial chain. ASML's attitude has hinted at the rapid development of China's lithography machines. China has entered the deep waters on the road of independent research and development of lithography machines. As long as it insists on being down to earth and moving forward step by step, the future EUV lithography machine will surely achieve a breakthrough, making it possible to counterattack and surpass